Free training provided by the HVAC School podcast is made possible because of the generous support from our sponsors, Testo, RectorSeal, and Carrier. Something that's been emerging lately, it's in the Unified Mechanical Code, and then a lot of local municipalities are starting to enforce this, is the idea of tamper-resistant refrigerant caps. And this is to prevent the theft and abuse of inhalants, primarily the abuse. Young people using refrigerants as a means to get a quick and easy high. And so it's a serious thing, and it's something that is emerging. You're going to start to see codes and local municipalities enforcing this. So what I would suggest is go ahead and start to get some no-vent caps from RectorSeal on your truck now, both on your installation crews and on your service vans. If you have to put on new caps anyway, maybe start using no-vent instead of the typical caps that you've been using. A lot of guys will point out, well, I don't want to have to keep that tool on my truck. Well, you're going to have to keep the tool on your truck anyway, because if your competitors use the no-vent caps, then you're going to need to have the tool anyway. And RectorSeal makes a nice little keychain key that you can put right on your key ring, and that way you've got it. And so once you start to use them, whenever you have cases where you've got caps that don't have seals, you can offer them to your customer as an upgrade. You can install them, and then it reduces the theft and the risk that an adolescent, especially, it's mostly young kids, are going to abuse the refrigerant as an inhalant. So that is the RectorSeal no-vent caps. You can find out more by going to rectorseal.com.
Meet ZoomLock, the 10-second flame-free refrigerant fitting from Parker. Reduce labor costs by 60% with no brazing, no flame, and no fire spotter. Discover how ZoomLock can help you be more efficient and productive. Visit ZoomLock.com for more information.
And now the man who uses "they don't make them like they used to" as a universal verb, Brian Orr.
Why, hello there. It seems you found the HVAC School podcast, the podcast that reminds you of all the things that you forgot about HVACR, or maybe reminds you about a few things that you forgot to know in the first place. My name is Brian Orr, and I am your pretend internet professor of HVACRology. And today on the podcast, we have Jamie Kitchen, and Jamie is a multiple-time return contributor to the podcast. He's a very smart guy. He is a training manager at Danfoss, as well as an account manager. And we wanted to just talk about variable speed technology, sort of a 20,000-foot view, not quite a 50,000-foot view, but a 20,000-foot view of variable speed technology and kind of the why behind it. Variable speed gets a bad rap sometimes, and sometimes it may be deserved, but in this podcast, we're going to talk about it broadly, and then in the future, we're going to do a podcast maybe talking about some of the specific diagnostic elements. Here's something I want to say just as a kind of overarching statement about diagnosis. When it comes to diagnosing very complex systems, your best bet for learning how to diagnose them and learning about them is just reading the manufacturer's information about that particular product. So you have to know generally how things work and why they are the way they are, sequence of operation, how it's supposed to work and why it does what it does, what the objectives are. But once you know that, then your specific manufacturer is going to do it in a different way, and they're going to have different codes and so on and so forth. You have different error codes that are going to pop up on screens and how you get into different interfaces and all that sort of thing. It's going to be very specific to the manufacturer. So in those sorts of circumstances, it's best for you to go and get factory training or read the manual. So today's episode is all about variable technology. We kind of start talking about blowers, but then we go into talking about all the different elements of variable speed technology. And here we go, Jamie Kitchen. I think at this point, it's been like 4 or 5 time returning guest on the HVAC School podcast. And today we're going to talk variable speed blower technology. So thanks for coming on the podcast, Jamie.
Oh, thank you for having me.
Let's start here because you've done a lot of training on variable speed technology, and obviously Jamie's with Danfoss. And frankly, this is just a weird place to start here, but I'd like to understand what types of products does Danfoss have that relate to this whole world of variable speed motors?
There's a couple of things. I mean, you have the direct ones, which are the piece of equipment that's actually being manipulated or driven by a variable speed drive. And that usually comes down to fluid pumps, gas pumps, such as compressors, and of course, air side. So the control of fan motors, blower motors, things like that. So those are the ones that are actually actively being driven. The other side of that, of course, is the controllers, which need to react quick enough to get information back so that you can kind of do real-time modulation based on inputs coming in, your sensors. So part of that's going to be your electronic expansion valves, the sensors and all that kind of stuff that go along into feeding the information back. Because if you change the speed of something and you do that based on either outdated old information, in other words, it's more than a few seconds old, or your equipment can't respond properly to the reaction in the change in air, say you're using the slow acting TXV, then you're actually going to hurt more than you're going to help. So all that kind of comes together as one package. So we just don't offer somebody a variable speed compressor unless they can back up that compressor with the controls and the adaptive metering devices that support it along the way.
Yeah, and so I think a lot of technicians, they think in terms of like a particular brand, like they'll think Carrier or Train or Lennox or whatever. But obviously Danfoss is providing solutions to the actual manufacturer. So you'll see Danfoss valves and Danfoss compressors in certain OEM packages, and then you'll also see them on the shelf for replacement components. I mean, the other day I worked on a Danfoss variable frequency drive on a Walmart. And so there was the Danfoss component that then interfaced with the other controls, and the variable frequency drive in that particular application was working with a Hill Phoenix rack. So you have these different OEMs, but then you have in that case, the variable frequency drive outside of that. But then you also have some particular solutions that OEMs also use. But I think the first thing that I want to address here is that most technicians, when they think of variable frequency or when they think of variable speed, they're generally going to start by thinking about typical residential blower technology. So they're going to think about, variable speed. Well, that's a ECM blower, a variable speed blower, or maybe even think about an X13. So do you have much experience with that where you can kind of segue between what those products do and what some of the more advanced, especially on the commercial side, how those function?
Well, yeah, sure. It's absolutely easy because they all do essentially the same thing. First of all, you have to ask yourself, what are you trying to accomplish? What do I need? What are my goals that I can't achieve with a constant or fixed speed setup? So I guess we need to kind of start with, let's take a couple scenarios and look at what the challenges are with a fixed speed. And then we can kind of contrast that with variable speed and where we can kind of have our cake and eat it too, so to speak. I mean, you addressed residential HVAC. Let's take a look at that. So, you're down in the Florida area where dehumidification is key. Yes, you have high ambient temperatures, such you have high dry bulb temperatures, but at the same time, along with those, you have high moisture levels, high relative humidity. And RH is kind of, as it says, relative humidity. And as we talked about earlier on our earlier podcast dealing with humidity, how much moisture the air holds is relative to its temperature. So at a 90 or 95 degree day, the air can hold so much moisture that the latent component, the latent heat of the air is like off the scale. You can't even plot it on a standard psychometrics chart unless you use a high temperature version of one because the energy levels are just too high. So what do? Well, you set up your airflow at, say, 350 or 320 CFM a ton. You drop your evaporator temperature and you have a highly latent focused process. Unfortunately, this is a necessity because it is not efficient. If you were to take your unit that's operating with, say, a 38 or 36 degree evaporator temperature and you compared it to a 45 or 46 degree evaporator temperature, you're going to use probably 15 or 20% more energy doing your cooling. Now, because it's an absolute requirement, we need to go that route. But here's the thing. How many days of the year is that low CFM, low evaporator temperature ideal for the conditions? I'm just going to go out on a limb here and say maybe 50% of the time or 40% of the time. The other times of the year, you could get by with a higher evaporator temperature, higher CFM, achieve more energy efficiency through higher COPs, and save energy and get better comfort cooling, where you're not over drying the air when it's not really necessary. So that's kind of one side of it. The variable speed, it allows you to measure the outdoor conditions, measure the indoor conditions, and essentially measure what your system is doing almost live in real time. And it'll say, okay, right now we have relatively low ambient temperatures, but high moisture levels. So we can treat the air this way. Later on in the day, when the sensible heat portion climbs up, and it may not be a highly wet day with high RH, we can bump up the CFM a little bit, increase our coil temperature, and away we go. So we either spool the compressor down, we spool the fan up. Our electronic expansion valve is always looking for the optimal superheat anyway, so it's just going to do whatever the requirements tell it to do. And now you're running the system in a far more ideal situation. Then as the nighttime goes by and your sensible load drops off, again, it can tailor the system to run. So it's really this smart way of doing it rather than taking one profile and applying it 365 days of the year. Let's look at another analogy. Let's look at defrost. If you have timed defrost, it's not bad. I mean, you run your defrost for 3 or 4 hours. It defrosts the evaporator coil in refrigeration, say, and you're good to go. But that time defrost in the summertime, if you set it when it's cool outside and there's not as much moisture, you're going to under defrost in the summertime if you set it up when it's cooler. If you set it up in the summertime, so you have long defrost times to handle all the ice buildup in the summertime, during the winter months or the cooler months, you're going to over defrost and you're going to waste a ton of energy. So it's not ideal. You pick a certain one and you stick with it. Unless you physically change it, it's going to stay that way.
So like as a general overarching principle here, what we're doing when we're talking about variable speeds, in general, we can vary the speeds of lots of different things. We can vary the speeds of compressors, condenser fans, blowers. In the case of the Walmart I was mentioning earlier, I was working on the condensing fans. And so that has to do with outdoor ambient conditions. So there's a lot of different things you can affect with variable speed technology. And really what we're doing here is we're making sense of non-optimal conditions where when you have a fixed speed situation, you're not optimizing for varying conditions. And so as a general rule, I guess, let's just pin this down and see if you agree with this, that variable speed technology as a whole is designed to handle situations in which the conditions vary in one way or another. Is that fair?
Yes, absolutely. There's two sides to this. One is the flexibility that you just mentioned and I was driving around earlier, but there's also the capacity factor. One of the things that we learned early on that, to be honest with you, surprised the heck out of all of us was when you look at the load on a building and you do it with your degree days, you do it very accurately, and you think you have this accurate heat profile for your building. What we found was that when we put a variable speed system in that had a similar capacity to the fixed speed unit, it only ran at the rated capacity of the fixed speed unit. In other words, let's say you had a 20-ton fixed speed unit. It only ran at 20 tons. Are you ready for this? For 3% of the time. 3% of the time. So we have these drastically oversized units. And not only are you compromising proper air treatment when you vary away from the optimal conditions, but at the same time, you're cycling these units far more often than what you should be to give yourself effective cooling. When all the extra energy use that comes from starting and stopping these units, it's incredible. So it's a two-pronged approach. Number one, if you're going to have a fixed speed unit, you got to oversize it so stupidly big because you got to be prepared for that day and a half or 2 days in early August when it hits 105 degrees and you have high humidity. On the rest of the days when it's 102 degrees and slightly lower humidity, you may think, oh, what's the difference? Well, the difference could be 15% difference in energy requirements or cooling requirements. That's a lot because that means you've got about a 5 or 6% difference in energy usage to cool that air that you're just throwing out the window. So to a residential person, what we're looking at is obviously better control, but also a greater savings on energy efficiency. And this goes not just for the homeowner, but for the utilities and everybody else that's providing this energy. We all know about brownouts, and probably the best way to avoid a brownout, to be honest with you, is a variable speed HVAC system.
Because you don't have those instantaneous loads of equipment going on?
Instantaneous loads of starting and stopping. You may think, okay, well, my unit only draws high current for a couple of seconds. Well, when you multiply that by hundreds of thousands of units starting and stopping, it adds a much higher percentage of energy requirements to the grid over those peak hours. And I mean, we're talking 20 or 30% increase in electrical demand just due to that, right? So to be honest with you, you can shave a ton of energy requirements off of the grid just by switching to this technology. And the savings are incredible, to be honest with you.
And that's kind of what I wanted to reveal. Like, I've spent a lot of time on this podcast and in articles talking about the differences between X13 motors and variable speed motors and variable frequency drives and that kind of thing. I mean, there's not that much to talk about. I mean, really, you're just packaging variable speed in different ways. So when you think about an X13 motor, we're really only solving one problem with an X13 motor, and that is the issue of typical single-speed PSC motors of producing less airflow as the static pressure increases. So by putting in an X13 motor, you help address that one problem. And in the process, you also help with energy efficiency. But you're not doing much else with that because there's not variable, it's just constant torque.
Yeah, I mean, what it's doing is it allows you to overcome certain limitations in the system or certain challenges in the system with ductwork and things like that. And of course, no technology is ever going to come bad workmanship or bad install or whatever in ductwork or on the air side. But there is definitely a value in it in making sure that something is constant in the system. The air side is probably one of the most ignored sides of our industry. And it's really tragic because I've heard multiple times people tell me that no, if you don't know your airflow, then any other reading you take is going to be useless, right? So it definitely addresses that one side of the equation.
So I don't want to downplay it. So whenever I say X13 is a good technology, people just start freaking out on me because there's been some technical problems with X13. So of course, whenever you have a product that has a technical problem, a failure, I think largely they've gotten a hold of. That doesn't mean that it's a bad technology. It just means they had a few bugs to work out. I think X13 is a great idea. And it helps solve the problem that you just mentioned, which is airside output, making sure that you're actually producing the CFM that the system was designed for, even in less than ideal conditions. And it's a more efficient motor. It actually uses electrical energy more efficiently to produce airflow output. So that's another advantage to the X13.
Absolutely. 100%.
And so then you move on to ECM, and ECM just kind of ups the ante because now an ECM motor has the ability to, on the fly, make adjustments to airflow based on some sensor input. So sensor input most commonly being dehumidification or equipment staging. So you have multiple stage equipment. It can affect the inputs and tell the motor, all right, this is the CFM that we need to produce, and make those changes on the fly. So just like you mentioned, instead of always producing 320 CFM per ton, it can produce 400 CFM per ton until there's a high latent load, high relative humidity in the space, and then the thermostat drops, in most cases in residential equipment, it drops the DH call or decall or dehum, whatever the piece of equipment is, and the equipment now knows, okay, let's drop down to 320 CFM because we know we have high latent load. That technology's been around for as long as I've been in the trade, so almost 20 years, and that's a really nice feature. Unfortunately, it gets set up incorrectly in a lot of cases. But that's really the only extension of X13 in that particular application that I can think of. Can you think of anything else?
No, I think kind of nailed it in the head on that one. I mean, that's really the overarching reason for it. So
you're using sensors, but you're using like a sensor in the thermostat that really is just an on-off. It's not really having granular communication with the equipment about real-time humidity readings. It's just saying, all right, we have high latent load or we don't. We need to dehumidify or we don't need to dehumidify. And of course, there are additional technologies that do a much better job of that. And do you have some examples of that?
And this side is your air side, outside, inside, and the before and after, or, the return supply conditions. So having something that actually gives you a wet bulb reading or some indication of humidity in the air is huge because let's face it, we're in a dry bulb driven world, right? That's what your thermostat on the wall reads. It's dry bulb. And if you have high humidity in the air, you better hope you have a dry bulb load as well, like a warm ambient that's going to drive that system to dehumidify. Otherwise, you're not going to get anything unless you overcool your space. So right then and there, having that ability to measure wet bulb is huge. That's a big step up. On top of that, the next step is some of this may deal a little bit more with the commercial side of stuff, but it's just having that before and after. What is the condition leaving my coil? Because that change in the air going over your coil is really going to indicate what you're going to do to the space. And if it says, I don't have this need for this high latent heat removal, but right now I'm scavenging a ton of moisture off my coil, I better do something about it. So it'll speed up the fan. It'll slow down the compressor a little bit. It'll do multiple different things. and you're really getting more of a dynamic response to what the coil is doing to the air compared to what the space needs. Let's take a typical situation. You do a heat load on a house or any dwelling. You take the outside conditions, you take the inside conditions, you do a bunch of different things, and then you says, here's my heat load. Well, we're doing that one step further. We're taking that heat load and we're breaking it down into sensible and latent. So yes, you might have a certain amount of moisture inside the space, but if it detects that it's either dry or really wet outside, and combine that with the temperature, if it's 20 degrees warmer outside than it is inside, and it's at the same RH level outside, that means the air probably holds 30 or 40% more moisture than it does inside. So it takes that information and says, okay, I need to make sure that I have a drying focus here because I'm going to be bringing in a whole bunch of moisture level and a whole bunch of moisture over the next few hours. And I need to deal with that. So it's almost like you're dealing with it on the fly. You're actively setting your system up so that it's going to respond to certain conditions outside in anticipation of what's going to happen. Okay. And I like that idea of it. So to be honest with you, it's just a little bit more smart than just reacting to what the current condition inside is.
When you use a variable technology, which again, variable technology means that we can make changes based on changing conditions, either in the system, in the load, in the space, whatever it is that we're wanting to do. And when you think about things like a variable speed or a multi-speed compressor, for example, that's not necessarily what this podcast is about, but it's a similar concept. You also have to have a variable speed blower that adapts to what that compressor is doing, because otherwise you're not going to have a coil temperature that remains stable. And so in the past, what we've done is we've done just the blower without the compressor. And so we don't have a stable coil temperature in a lot of cases on purpose, because we're trying to drive down the coil temperature in order to remove more moisture. But when you affect that other side, you affect the compressor side. And if you were not to properly change the variable speed blower, then it wouldn't be changing appropriately. And you would see this fluctuation in evaporator temperature, which ultimately on the evaporator and blower side, that's a lot of what we're wanting to do. We're wanting to hit a target of CFM output for whatever the conditions are. And then we're wanting to hit a target coil temperature, which means really a target flow of refrigerant, target pounds of refrigerant being moved through that evaporator coil at a given time. Just as a summary, before we get started on sensible latent and all this, I want to just lay down what these things are. We talk about this in a past dehumidification episode with Jamie, so go back and listen to that for a full understanding. But when we say latent load, we're talking about moisture load. So we mean the moisture in the air. We're talking about relative humidity of the air when it comes to comfort. And when we talk about dry bulb, we're talking about the temperature that you see on the thermostat, on the thermometer. That's sensible. That's what you see there, and that's dry bulb temperature. When we say relative humidity, we're talking about the humidity that's in the air relative to its temperature. So air that is lower temperature can hold less humidity. So air with the same grains of moisture in it at a lower temperature would have a higher relative humidity relative to how much it can actually hold. And we're also going to touch on sensible heat ratio. We're going to mention that. And whenever we say sensible heat ratio, you'll see that in equipment specs. You'll see it on plans sometimes. You'll see SHR. Sensible heat ratio means how much of the total capacity of this equipment under these conditions is sensible and how much is latent. So if you had a sensible heat ratio of 0.7 or 0.70, that means that 70% of the capacity is going towards sensible, changing the temperature of the air, and 30% of it is going to latent, which means changing the moisture content of the air. Did I miss anything there on the summary?
No, not at all. It's like a pivot point, and you hit the nail on the head. It'd be interesting to know if most people know what their actual system is doing. Because to be honest with you, we learned this back in school, sensible heat ratio. And I'm just trying to think how many times I actually have applied that down the road. I know if I'm trying to figure out what a system is actually doing as far as cooling the air, you can't beat a sensible heat ratio. But you need to back that up with the manufacturer's literature, because they're the ones that's going to dictate what the unit should be doing. Let's think of it this way. When we were talking about humidity back in the day, I actually mentioned, when we eventually get to cut the variable speed, I want to cover this. If you happen to have a load on your evaporator, and whether it's a TXV or an EEV will give you a slightly lower superheat. But here's what's going to happen. The meter device with a fixed fan speed and a fixed compressor speed, when it hits that latent load, the EEV or TXV doesn't give a care whether it's latent or sensible heat. It sees that extra heat. If the fan speed is constant, in other words, is getting a certain amount of load across it, it's going to need to open up to match that load. If you have a fixed speed compressor, the first thing that's going to happen is your suction pressure is going to drift up, because that's the only way that fixed speed compressor can pump that extra refrigerant that the metering device is putting in. As soon as you start to raise your evaporator temperature, you start to reduce your latent heat removal. So what happens is you find a balance point where the higher evaporator temperature has actually reduced the heat capability or heat absorbing capability of the evaporator, mostly in the latent side. You've compromised your dehumidification, and you've balanced at a point now where you're not really accomplishing anything good on either side, sensible or latent, right? You've got a higher evaporator temperature. You're not pulling as much moisture out of the air. The only thing you can do now is to overcool the space to try and get that latent load out. Ideally, what would be better is, why don't we just reduce our airflow a little bit, let the TXV throttle closed or EEV throttle closed, drop our evaporator temperature a little bit, and now we're running in much more of a latent focused load. So we might still have 80% of the load we had before on the evaporator, or even 90%, but we've gotten rid of a big chunk of that sensible load, and we've replaced that with latent load. Now you may ask me, well, hold on a second. Our evaporator is actually colder compared to the space temperature. So why did we get rid of sensible load? Well, we never got rid of sensible load, but the latent load increases for every degree you drop your evaporator temperature compared to the air. The increase in latent heat removal is far greater than the increase in sensible heat load. So your end sensible heat ratio is much smaller. In other words, you might go from 30% latent load to 45% latent load just by dropping your coil temperature a few degrees and bumping down your CFM by 30 or 40 CFM. It's amazing how quickly that will change. Alternatively, if you do still have a high sensible load, because it's 95 degrees outside and a high latent load, just keep the TXV open the same amount, or let it feed more in, and then you can spool up your compressor an extra 10 or 15 hertz. Now, you're not necessarily going to save energy doing this, but you're going to be able to ideally match the requirements when you have both a high sensible and latent load. So you have this huge flexibility of how you can treat the air. We have some limitations on the residential side because we don't use reheat, and I'll talk on that in a second because it's very important. But either way, I still argue that you're almost overcooling the air if you have it set up for latent heat removal, because the air is coming out a lot colder than it would if you had it focused on sensible heat removal. And people can still report it being drafty. But here's the catch. If you happen to have a smart thermostat, it should have algorithms that say, look, if we drop our humidity in our space 10%, we can bump our dry bulb temperature up a couple of degrees so that it still feels the same comfort level that it would have been if it was 2 or 3 degrees cooler, but had a higher humidity level. You see what I'm saying here? The human experience is the same either way as far as your body is concerned. By keeping the space a few degrees higher and pulling more moisture out and keeping the relative humidity lower, we achieve the same comfort level without really using more energy.
Which is an interesting thing when it comes to human comfort, because there's a range of human comfort that you can affect by changing the dry bulb or changing the relative humidity side of it, and even changing the radiant heat of the space. That affects human comfort significantly. We've talked a little bit about that on this podcast and also on Bill Spohn's Building HVAC Science podcast. I think they call it mean radiant temperature or something like that. It was a new term for me, but it basically means the temperature of the surfaces around you. Whereas when you're talking about process refrigeration or grocery store refrigeration where you're cooling food, those also have a range, but they're more separate from each other. Like you have a range of relative humidities that are acceptable, and you have a range of dry bulb temperatures that are acceptable, and you really need to keep it in that range. Whereas with human comfort, we often think, well, I want it to be 75 degrees or 73 degrees or 72 degrees, but really, do you need it to be that dry bulb temperature, or could you just affect the relative humidity down from, say, 58% relative humidity down to 54 and achieve the same level of human comfort? And the answer is that often you can.
Absolutely. But again, there's so many factors in there that are going to affect it. It's going to be hard to probably find the right value for everybody. I know my wife and I are always arguing over the thermostat all the time because I'm always too hot and she's always too cold. But I don't think anything's going to fix that, to be honest with you. But from a ASHRAE standpoint, or from what we're trying to accomplish as far as getting something that's going to be acceptable to the most people, you're right on. If you control your humidity, you have a lot more leeway on the dry bulb side than what you normally would have. You're really handcuffed almost in keeping the space cooler if you don't have good humidity control. If you have high humidity in your space, you almost always have to have it several degrees cooler inside in the summertime just to make people feel cool enough to be comfortable. But there's that fine line where if it gets too cold with high humidity, now people feel cold and damp, right? And now they're really uncomfortable. So it's almost like you can't win either way without addressing that humidity level.
This is a very broad subject here. I mean, this applies to refrigeration, it applies to the commercial side, it applies to the residential side. Talk about the differences between what's possible in most residential comfort cooling applications versus what's possible in the kind of the breadth and depth of commercial.
Great question. We have a couple options here. Obviously, with residential, we're a little bit more restricted in what we can do. You may be bringing in fresh air. You may have a rotary heat wheel or something that deals with that energy coming in and going out and making the exchange. But if you look at it, let's just take your normal system, your average system. You've got a compressor, a blower, an evaporator, all that stuff, and you're running a constant amount of air across the evaporator. You've got a dry bulb thermostat on the wall that measures dry bulb, and if it gets hot enough in the space, bang, it brings on the cooling. Historically, in fact, not just historically, currently, we're relying on that dry bulb indication to bring the system on and run it long enough to do the dehumidification. So the dehumidification is kind of just along for the ride. It's never really been a focus. So if you take your region down there, you tailor the system so that it operates with much lower evaporator temperatures. So you have a latent focus compared to, say, up in the north, central, west, where you may have really hot days, but you only have probably half the humidity in the air that you have where you're located. So they would run a much higher evaporator temperature. So ideally for residential, switch out that dry bulb thermostat to one that's wet bulb. So in other words, it's almost like a total energy sensor. You're not just measuring wet bulb, but you're determining both, let's use that term relative humidity again. You're determining the relative humidity, how much moisture is in the air, as well as how warm the air actually is, dry bulb temperature. And it can say, okay, I have a dry bulb temperature that's relatively high, but I also have this ton of moisture that I really need to deal with. And if I deal with it right, I can let that dry bulb temperature stay a few degrees warmer than it normally would be. And what I'm going to do, instead of making sure the dry bulb temperature is low, I'm going to take more moisture out of the air. So what a variable speed system would do with that information from that sensor is it would fire the system up and it would make sure there's enough airflow going through just to scavenge all that moisture out of the air. And it might run a certain amount of time, dry the air out, without actually having to cool that space down to, say, 72 degrees. It might maintain 74 degrees in that space instead of 72, but keep the relative humidity 10% lower. So it allows you to have this whole flexibility there. So by varying the compressor and varying the fan, it allows you to tailor exactly the condition to the air that you want. You don't have to overcool the space to maintain a proper humidity level, which is what you almost absolutely have to do with a fixed speed system unless you decide to dedicate it to latent heat removal like you do in Florida. If you're in one of the states where you don't always have hot weather in the summertime, but you have wet weather, if you have a fixed speed system, what are you going to do? You either have to overcool the air to get rid of the humidity because you don't have this huge dry bulb load, or you just treat the dry bulb load when required and you leave this massive amount of humidity in the space and nobody's comfortable. So either way you look at it, it's not a good solution. With variable speed, take that dry bulb stat out of the picture, put one that measures both latent and sensible heat, and run your system to focus on the air treatment that's required. And that's really about as far as we can go with residential systems.
All right, if you guys have listened to this podcast for any amount of time, you know that I kind of have a little bit of a crush on the Testo 605i. It's just a stupendous, can I say stupendous and not have it seem like hyperbole? I'm going to choose to say stupendous. It is a stupendous tool for the investment that you spend on it. It is a great thermal hygrometer. And for those of you who are like, what the heck is a thermal hygrometer? Well, let me tell you. A thermal hygrometer is basically a digital psychrometer. That's another term for it. And it measures wet bulb, dry bulb, relative humidity. Dew point, it can extract all of those. If you've ever looked at a psych chart, you need a couple pieces of information, and then you can extract the rest. But what the 605i does really well is that you can measure these readings in duct. So you can take wet bulb, dry bulb, relative humidity in the return, wet bulb, dry bulb, relative humidity in the supply, and right there in the Smart Probes app, it will actually calculate delivered capacity as long as you enter the CFMs, which is pretty cool. CFM. I always want to say CFMs, CFM of air. So the 605i is a great tool, but when you add in what Jim Bergman is doing with the MeasureQuick app, which you can find out more by going to measurequick.com/download now on that application. I'm excited about that product. But the Testo Smart Probes and the Testo 605i work with Jim Bergman's MeasureQuick app. And so you can get the best of both worlds, a really, really highly functional app plus the Testo 605i. So the actual Smart Probe app that you can use directly with the 605i, it works great, but you can extend its functionality by using it with the MeasureQuick app. And so getting delivered capacity is a huge thing. I mean, you can actually show your customer right there on your phone. We've already done this on many occasions. Like, look, this is how much capacity this system is actually delivering. Here's what you paid for. Here's what you got. It's a great product. And it's also just a great way to get your indoor wet bulb and dry bulb, which you need anyway if you're going to calculate superheat on a fixed orifice system. If you want to use it to calculate target delta T, air temperature split, it's also great for that. It's just a good all-around temperature measurement device. Plus, it gives you that additional data that you can only get from a thermohygrometer, and you have the ability to get it in the duct. Plus, it's Bluetooth. And like I've mentioned a million times, you can get that particular product, the Testo 605i, by going to TrueTechTools.com. And at checkout, use the offer code GETSCHOOLED, all one word, no caps, no spaces, GETSCHOOLED. Look at the bottom left-hand side of the screen when you're in the process of checking out there, and there's a coupon code box, and you type GETSCHOOLED in there, and you will get a great discount. In cases where you have high latent load and you don't have high sensible temperature, and I think a lot of my friends in Ohio will say that that's how it is in Ohio often, you're really left with two options. You're left with the option of leaving it uncomfortable or making it uncomfortable.
Yes.
Either you leave it uncomfortable because of the moisture, or you make it uncomfortable because you're overcooling the space. Those are your options, unless you have that additional control where you can remove latent without adding significantly to sensible, which is a hard thing to do.
It is really hard to do because, I hate to say it, you're almost taking the human element out of it because you no longer can focus on that dry bulb temperature. People look at that dry bulb temperature and they say it's too hot in here. That is no longer going to apply. If you're used to having your house at 75 degrees and you see it's 76 in there or 77 degrees, your body isn't going to tell you, oh, wait a minute, it's 10% less humidity in here. I'm actually okay, right? Your brain's going to tell you, oh, it's too warm in here. I need to turn my thermostat down. But really, physiologically, your body is in the exact same environment as far as keeping itself comfortable as it was when the temperature was 2 or 3 degrees cooler, but the humidity was higher. It'll be interesting to see how that, I hate to say it, that human element plays out because we're so used to being accustomed to having control over it and making that decision. We'll have to wait and see what happens there. Unless we can somehow trick people, which I don't think is going to fly, it'll be interesting to see how that turns out.
What you're pointing out is what companies like Mitsubishi and their ductless line, they've done this for years where they say too hot, too cool. That's what the buttons say.
Okay.
And that's kind of adjusting. I mean, they still give you a number, but instead of saying, I want it to be 72, you adjust it and say, I'm too hot, or you adjust it up and say, I'm too cool. And that's interesting. We have to come up almost with a new language because it's not just too hot or too cool. I mean, it is, I guess, my body feels too hot or too cool, but it's not just the dry bulb temperature of the air. It's I'm uncomfortable on the low side or I'm uncomfortable on the high side is really what it is, because there are these three factors, and we're talking about the humidity factor primarily as it relates to variable speed and the dry bulb factor. But then there's also, like I mentioned before, the radiant temperature of the surfaces that are exposed to your body that also affects human comfort, as well as airflow. I mean, airflow also affects human comfort. So there's all these different factors that you can change one and it changes the perception of comfort, even with that dry bulb temperature on the wall being exactly the same.
Yeah. And without getting off track here, if your diffusers are dumping cold air down the back of everybody, I don't care what you have for technology in the system, people aren't going to be comfortable. And if you have a large window that sits outside, your friend in Ohio is probably going to feel pretty darn cold because they're losing all this radiative heat to that window in the wintertime, right? It doesn't really matter what the space temperature is. The side that's facing that window is probably going to think it's about 10 degrees colder in the room than the side that's not facing the window, right? So you really have to address the whole thing to make people comfortable. But from a residential standpoint, where you kind of have a lot more control over that, at least you should, I think you're right. That wall sensor that tells people the temperature, I like that idea. Too warm, too cold, because now it's more of a whole how I feel effect rather than just a number value. So on the residential side, you mentioned about overcooling the space. Your friends in Ohio would appreciate the fact that when it's 75 degrees outside and it's raining, in other words, it's 98% or 100% humidity outside, what really would help them out a lot is this thing called reheat. You have your little dehumidifier, and you take your dehumidifier, you put it in your basement where you have the real moisture problems. And if you look at what does a dehumidifier do? It cools the air, and then it runs the air through the condenser, which raises the temperature back up again, probably 7, 8, even 10 degrees above what it was when it went in there. So the air is coming out a bit warmer and a lot drier. And that really helps with the humidity because you don't overcool that space to dry it out. And it really accomplishes that with keeping people comfortable, spot dehumidification. Well, we can do the same thing with a air conditioning system, an AC system, by taking some of that air, running it through an evaporator, cooling it down more than we really need to, right? And then heat it back up again using heat from the condenser. And this is a great way to maintain the comfort zone in a building or a space where there isn't this large dry bulb load. Okay, so you use variable speed to slow the fan down or speed the compressor up or whatever you need to do to match the load. And then you overcool the air to pull the humidity out of it. And then you end up reheating that air back up again with free heat from that you're pulling off the condenser. And so when you take a step up to some of these more advanced systems, you don't really see that in residential too much now, I don't think, but you're definitely seeing it on the commercial side. And on the commercial side, this is really where it's starting to shine because there is such a huge opportunity for energy savings. And there is this huge demand for fresh air outside. And I don't know how much you've covered the need for fresh air now where you have these 100% fresh air makeup systems, but this is really where variable speed shines. So do you want to take a few minutes and touch on that then?
Let's do that. So we've talked a little bit about economizers and bringing in fresh air and some of the challenges, but I'm interested to hear about how variable speed technology is used in fresh air, and especially as it relates to, like you said, 100% fresh air machines.
If you remember back in the day, the old economizers, I refer to it back as the day when you had 3 refrigerants in your truck, right? Generally, the economizer was set up so that it measured the outside air. And there was this range of air conditions outside where if it was the right condition, in other words, it was cool outside with not a lot of humidity, you said, hey, free cooling. So you would bring this air in and you would exhaust the same amount of air outside or a similar amount of air, depending on whether you want to keep a negative or positive pressure in the building. And this would remove a big chunk of both your latent and sensible load. But the challenge is that the outside temperature doesn't really stay where you want it to stay. So economizers work great when the air is at the right condition, but that's really a narrow piece of time, depending on where you live. Some places you'll be able to use it more than others, but it is still limited. That is irregardless of the need for fresh air in a building. The need for fresh air in buildings is going up and up and up for multiple reasons. You need to bring that air in regardless of what the condition is, whether it's 95 degrees outside with high humidity or whether it's 10 degrees outside and bone dry. You still need to bring that air in and treat it. So what you have is this huge range of treatment requirements. Even from starting in the morning to the afternoon, you can have a completely different requirement for treating that air. And it's not a small requirement. The loads are enormous or can be enormous if they're not treated properly. So with variable speed, what you're really doing is you're measuring the indoor conditions, you're measuring the outdoor conditions. There are some algorithms in the controllers that compare these two, and they say, okay, here's what I need to do to treat that air So that's going to be exactly what I need to maintain my inside conditions. This is what I want inside. This is my ideal conditions. This is what I need to do to that air to treat it. So in the case of a day where it's relatively cool outside, let's say 75 degrees, and it's pouring rain, now you need almost a complete latent focus on that air coming in. So you run a slow fan speed, probably very similar to what you would do in Florida. You don't even need to treat all of the air. You may siphon off a portion of this air coming inside, treat a certain amount of it, and then inject it back into this fresh air space so that when it mixes, that air is exactly at the condition it needs to be. So there is no fixed treatment. It is changing all the time. And if you don't have a high sensible load, you are going to overcool the air even if you do have a latent focus. Even if you are running 320 CFM and a 36 degree evaporator temperature, the air coming out is going to have so much sensible heat removed from it, it's still going to overcool the space. So what do? You run it through a reheat coil using heat from the condenser that you would normally eject into the air. So you are really tailoring your fan speed and your compressor speed to maintain that evaporator condition to pull all that heat out of the air, to pull that moisture. And then you use a certain amount of reheat gas to reheat that air back up again. And in the end, the variable speed makes sure that all the conditions, the air, the compressor speed, the amount of refrigerant the compressor's pulling out of the evaporator to maintain the temperature, all that is completely aligned with what you're trying to accomplish in treating that air. So in the morning time, we might reflect what we're just talking about. In the afternoon, when the temperature goes from 75 to 95 degrees outside, oh heck, now it's complete. We're going to run this system at 95% of its capacity. We're going to run it with a higher evaporator temperature. We're going to run it with a higher airflow. And we're going to treat the air once again exactly as it needs to be treated to treat this air coming in. And you can say the exact same thing about the indoor air as well. But really, this requirement for outside fresh air, if it's not done right, the cost becomes prohibitive to be able to do this effectively. Because really, I hate to say it, is what you're really doing is bringing air in, treating it, and then ejecting it back out again. You can use heat pipes and rotary heat wheels to retrieve a lot of that heat that you're sending in and coming back out again. And that's a whole other area. But in reality, it's like you're taking heated water in and then you're throwing it back out the door again is really what you're doing. So you want to be able to do that as efficiently as possible so you're not basically flushing money outside along the way.
Yeah, so the variable speed technology is a huge part of that because it helps balance the equation so that you're not overcooling, so that you're not decreasing or increasing the sensible state inside the building if it doesn't need to be. Another thing I wanted to mention is that you mentioned using the condenser for reheat, but that isn't the only form of reheat. I mean, there are machines that use fossil fuels, gas. You could potentially use hydronics. And another thing that we see a lot in grocery stores is they use reheat off of the refrigeration condensers. The actual rack system, that's the reheat that they use for the store air, which is another interesting way of doing it.
Yeah, absolutely. Because again, it's free heat that you would otherwise have to pay for or that you would just flush outside to get rid of. So you actually find a use for it. That's great.
And it depends geography to geography. Obviously, down here in Florida, you're not going to see much gas reheat because we don't have outdoor conditions that require it. But one thing that I think is interesting just from a futuristic standpoint, 10, 20 years ago, we weren't talking about all of this different variable speed technology that can be used in order to match conditions perfectly. And one thing that everybody feels is fixed right now, they feel the need for fresh air is completely fixed, right? That's generally how people think about fresh air. You have so many slated occupants, you have so much square footage, there's a certain use case, and so you have to comply with this particular fresh air requirement. But a future's coming as sensor technology gets better where the fresh air that needs to be brought in or the outdoor air that needs to be brought in will be controlled based on CO2 levels, based on VOC levels, things, actual real-time indoor space conditions that will then control and limit the amount of unnecessary outdoor air that we would have to bring in based on the actual conditions in the space, which I guarantee you in the next 5-10 years, we're going to start doing a lot more of that.
Makes absolute sense, having better control over it. But, from a technician standpoint, the challenge is obviously understanding these systems, understanding how they're supposed to work, and of course, understanding how to service them when they don't. And I always shake my head whenever you talk to people who are also in positions who should know better, or at least understand, this is not a static field. This is continuously changing, just as much or more so than any other technical field, because it's being driven by, as you said, the availability of new technology, which allows us to do things we couldn't do before, combined with legislation. And the technology allows us to meet these new legislative requirements. And the catch is, once they go out there, somebody has to know how to install them correctly, commission it properly, do proper preventative maintenance on it to make sure it remains doing what it's supposed to do, and service it when something goes wrong. And the biggest holdback to the adoption of variable speed that we get, like when we go out to manufacturers, when we go out to people who could utilize this technology, you know what the biggest pushback we get is? Who's going to service it? Is there a technical body of people out there that understand this technology that can service it? Because it doesn't matter how good Siemens or Danfoss or anybody else makes the technology. If it's put out somewhere and it breaks and nobody can fix it or know how to maintain it, what ends up happening? It just gets jumpered out, or it becomes more of a drag on the system, more of a liability than it ever is a benefit. So there's this huge demand for education and training in these new technologies. So if you work in the field, my recommendation or my advice to you is to seek out places where you can receive training on this from the manufacturers, from companies like Carrier, Daikin, and that, because it's coming. And any training or education that allows you to do something you couldn't do before is an opportunity. So jump on board as quick as you can, because this is something that's coming and it's going to be around for a while. Really, if you can understand it, you can service it, you can install it, you have a great value to people who need to do this kind of stuff.
Yeah, the first thing that's required for people to do a proper job is to understand why it's a benefit. Because the reason why people bypass a economizer, you see economizers bypassed all the time.
Well, half the time they're rusted shut, but yeah.
Well, true. So there's reasons for that in some cases. But if somebody goes in and they bypass an economizer, or they throw a variable frequency drive into bypass, they're doing that because they've been taught, they've been told, they believe that there's no benefit to it, that it's a waste, that an engineer over-engineered something. And don't get me wrong, I've been a guy who's done this, and sometimes it's true. Sometimes systems are over-engineered from time to time. But in general, you have to understand the benefit. It's the same thing with maintenance. Technicians who don't believe in maintenance don't do a good maintenance. Technicians who do the best maintenance are the ones who believe in its value. So let's just do a quick list here and hit the things that we've discussed. So that way, those of you out there who are listening who are like, I'm still not a believer. Here's why variable speed technology is important, why it's here and why it's going to continue to be here, and why it's going to continue to be the future. In residential, we see this first and foremost with airside output performance. So those of you who love the old PSC motors and think X13 and ECM motors are a waste of time, I'm telling you that if you look at the fan curves, you look at the ability for these systems to produce the designed airflow output, they do a much better job. And it's really good for systems when the system is producing the amount of airflow that it's designed to produce. In the past, there were pieces of equipment out there producing 250, 270 CFM per ton, not because they were set up that way or because somebody was trying to get extreme latent capacity out of it, but because they just had really bad duct systems, really bad airflow setups, and that's what they were producing, which resulted in compressor problems, oil issues, freeze-ups, all kinds of issues that we didn't want to have, poor efficiency of the systems. And so these airside output performance aspect of variable speed technology, especially with ECMs and X13s in residential, is a real benefit. Anything you would add to that?
No, absolutely. You hit the nail on the head. Understanding it and seeing the value in it can be a real driver to getting involved and learning how it works. I mean, the two are really side by side. To have an appreciation of something, you really need to know. I hate to use a shoe, walk a mile in its shoes, but that's kind of what you're doing, right? What you just explained. If I can see the value of this to my customers, then it behooves me to make sure the system is running correctly. If they buy a SEER 21 system and it's not set up correctly and they're only getting SEER 12 out of it, really? They paid all this extra money for something and they're not seeing value for it. And that's a real tragedy because it just causes disillusionment with the industry all the way across. And that's not a road we want to go down.
The next thing that I want to mention that you mentioned, which is a really good point, is the instantaneous loads. So instantaneous loads, the startup power consumption that a motor draws, it requires you to put in larger wire. It puts a strain on the electrical grid nationally, but then also from the consumer standpoint, starting and stopping of devices uses power. And it also creates additional stress on the equipment. I mean, the greatest stress on a motor is when it's first forced to start up. And so a soft starting motor is a motor that's running cooler, it's running more efficiently, and it's not having those instantaneous loads. That's another benefit to variable speed technology that exists pretty much across the board. The next thing that I want to mention is comfort bandwidth, and this is actual dry bulb temperature bandwidth. With variable speed technology, you don't have to keep bumping top and bottom of the limits. You don't have to be running a 3-degree temperature bandwidth. You can nail it directly on a set dry bulb temperature if you want to, which is a benefit from a comfort standpoint. Because when people are in a space and the temperature keeps changing up and down 3 degrees, they're going to be uncomfortable. That's just because the condition of the space keeps changing on them versus nailing it right in the center of that zone, which you cannot do with a fixed speed piece of equipment. I mean, it goes up. If you have it set at 75, in the very best circumstance, it's going to get up to 76, turn on, go down to 74, turn off, and just keep bouncing up and down. Where 3-degree bandwidth is a pretty tight one. You may even see as high as 5 or 6 in some cases, depending on the control, which is also a huge factor with human comfort and with efficiency, because the tighter you set that bandwidth, the more inefficient the system is, because the more it's going on and off.
With a fixed speed system, absolutely, yes.
The next thing is dehumidification. Systems that are fixed speed, they don't have that dehumidification control. You can't alter the evaporator coil temperature away from what the conditions dictate. So when you have a system that's fixed speed, the conditions, the indoor outdoor conditions are going to dictate what that evaporator coil temperature is, and it's going to fluctuate with changes in those conditions. Whereas with a variable speed system, you can pick the evaporator temperature you want. You can pick it at a lower temperature if you want in order to dehumidify better, which is going to result in better human comfort. Because a thing that we often don't control as well as we could is relative humidity. And that's a thing we can do that really improves human comfort, which we talked a lot about, obviously, in this podcast. The next thing is capacity matching. So the ability to match the capacity of the equipment directly to the load, which is the same thing as comfort bandwidth. It's just another way of thinking of it. The optimum way to run any appliance is to match the capacity of the equipment perfectly to the load of the equipment. And this is true of residential refrigerators. This is true of even things like gas furnaces. I mean, a lot of people don't think of it in gas furnaces, but if you can match the output of a furnace directly to the load in the space where it just runs consistently at that point, you're going to have better comfort and you're going to have better efficiency in one sense, because you're not constantly bouncing up and down the differential between the indoor space temperature and the outdoor space temperature, which does help optimize. Now, when you talk about fuel consumption and all that, that's a whole nother topic, and you may not always be getting maximum efficiency on fuel consumption in those cases. But from a comfort standpoint, it's always best to match capacity to load. Is that correct, or would you add any caveats to that?
No, absolutely. Specifically with air conditioning, we have covered pretty much all of, I guess, the basis with air conditioning. I know this podcast is primarily air conditioning focused, so I think we've covered all the ins and outs of that. If I could just add one thing for those guys out there that do cover a little bit of refrigeration, remember variable speed fan control is also great on a condenser. Because when you have a single fan on a condenser, say, for example, for your walk-in box or the ice machine that you use in the hotel if the condenser's outside, there's real issues with changes in outside temperature. And take an ice machine, for example. If the condenser sits outside, the ice machine might only make half the ice when it's 30 or 40 degrees outside than it would when it's 90 degrees outside, because you can't build enough condensing pressure to feed it properly. Well, you throw a little fan control on there, a little variable speed fan control, you can slow that fan down 30%, and you can remove the same amount of heat you would remove on a summertime, maintain that condensing pressure rock steady. And if you maintain a condensing pressure rock steady, that means you're going to have a continuous feed through your metering device. Your evaporator temperature isn't going to fluctuate away from what you want. It allows you to make things like ice or freeze product or even dehumidify, going back to the HVAC side of things. And at the same time, it saves a ton of energy. So it really allows you to have a much wider operating range with the condenser than you normally would with a single fan off and on. It also gets rid of things like flash gas that occur when you cycle your condenser fans, causing erratic feeding of the meter devices due to flash gas. All that can be eliminated by putting a little variable speed fan out there and eliminate the need for a holdback valve. Instead of backing up refrigerant in the condenser and reducing your condenser capacity by 60 or 70%, why don't you just reduce your airflow by 60 or 70% on the condenser and do the same thing. So again, big savings, a lot of flexibility. You're probably going to see this technology coming down the road. So really, variable speed offers us a lot of flexibility, whether it's hydronic pumps, whether it's airflow in HVAC or refrigeration systems, whether it's tailoring that airflow for the different types of day and doing the same thing with the compressor. Really, again, it allows you to have your cake and eat it too. Let me just end it there.
Absolutely. Sounds good. Yeah. And obviously in this podcast, we didn't get into like the specifics of how variable speed technology works. And I've done a lot of articles about that, and it really isn't that complicated. I mean, in some cases, we kind of overthink this stuff, and we'll do a podcast in the future where we address that specifically. This is more so about talking about applications, why it's a good technology, and what you can do with it. I think we've hit all the high points and beat all the dead horses. So,
but, try and look at it as an opportunity for the industry and for yourself too, as well. It's one of these things where if you keep adopting to the new technology, your job can't be outsourced. You have job security, right? The more you know. So as an educator and as a trainer, I guess I view things from this standpoint to those individuals out there. Don't look at it as, oh, this is so ominous on me trying to use or ponderous to use. Try and look at it as an opportunity. Learn more about it. Become that guy that people call to go out and service this stuff. Because again, you can't be outsourced. Your job can't be automated. So really, if you're looking for job security, you can't beat this.
And again, for those of you who have been frustrated by some of the technologies in the past, as far as the reliability or servicing issues, recognize that anytime technologies are new or newer, there's always going to be bugs that get worked out. And so just because there's been problems with particular products or issues that had to be overcome.
Microchannel, remember that?
Right. Well, I think some of those issues may still exist there, and they probably still exist in some variable speed technologies, but it's going to get worked out. I mean, I remember when Trane came out with the Trane 1500, I think was like the first variable speed scroll on the market, and they had all kinds of issues with that unit. But now one of my favorite products on the market at all, probably my favorite residential product on the market, is the Carrier VNA8, which uses a 5-stage rotary compressor in the condenser, and it's what I have in my house. I love the thing. They work out the bugs over time, and you'll find products that you like and products that you have challenges with. It's interesting, even Bosch has a really interesting new condenser that they're using sensors in a different way, where they have a variable speed compressor, a drive-driven compressor, and they can use it with a fixed speed blower. Now, you don't get all the dehumidification benefits and everything, but you still get some of the efficiency benefits of that variable speed compressor. So there's really some interesting new technologies out there. Some will work, some won't work as well. And that doesn't mean you throw the baby out with the bathwater. That's my encouragement to techs out there. Still learn it, be the expert in it. That's how you're going to really excel in the trade.
Yep, agreed.
All right, Jamie, thank you for your time. Once again, I really appreciate it. I think this is really helpful, and hope to talk to you again soon.
Oh, same here. Thank you for having me on. Talk to you soon.
Hey, thanks for listening to the whole podcast. Thanks for being part of what we do here at HVAC School, which is provide free training for people who are in the business, either in the business currently working in it, or maybe retired out of it or moved on into management and kind of want to keep up on what's new. And then also those who are coming into the business. So those who are apprentices or in trade schools, we are a resource. And I've had a lot of people ask, so where's your school? Well, we don't have a physical location. Not to say that I would never have a physical location, but at this point, we're just a resource for people who do this sort of thing. You cannot learn how to fix air conditioning and refrigeration systems by listening to a podcast alone. You have to do it with your hands. You have to actually do it. But for those of you who are doing it, hopefully this is a good resource to help you maybe think of some things you haven't thought of, or maybe think a little more deeply about some things you've been doing for a while. That's what we're here to do. Now, we're proudly a member of the Blue Collar Roots Network. You can find all the shows that are in the Blue Collar Roots Network by going to bluecollarroots.com. A couple shows that I really like is the Tool Pros podcast with Brent Ridley and Billy Noth. They've been having some really great guests on lately, talking about all kinds of different things in the world of tools. Bill Spone with the Building HVAC Science podcast. He always brings the technical knowledge every single time. I learn something every time I edit and produce his podcast. Very thankful to Bill. He's a good friend. Speaking of Bill Spone, if you want to find great tools, you can go to TrueTechTools.com. Use the offer code GetSchooled for a great discount on all the tools that they have. Bill is one of the owners, the primary owner of TrueTechTools.com. And then finally, Tersh Blissett and the Service Business Mastery podcast, which talks all about service businesses, how to run them well, all the top tips and tricks and tactics. And Tersh actually has some interesting news coming up in his personal and business life that's going to, I think, take the podcast in a new and exciting direction. So make sure to check that out. You can subscribe to all of those by going to the podcast app if you have an iPhone, or if you have an Android device, you can go to the Stitcher app, you can go to the Google Play Store, you can go to, there's a whole bunch of different apps where you can listen to podcasts, and we should be on all of them. So once again, thank you for listening. So the other day, I was just walking by an alleyway, and this guy calls me over, and he tries to sell me some shoes, and they look like pretty good shoes. Normally, I don't buy shoes from shady-looking characters like that, but I bought them. I'm not sure what he laced those things with, but I've been tripping all day. We'll talk to you next time on HVAC School.
Thanks for listening to the HVAC School Podcast. You can find more great HVACR education material and subscribe to our short daily tech tips by going to hvacrschool.com. If you enjoy the podcast, would you mind hopping on iTunes or the podcast app and leave us a review? We would really appreciate it. See you next week on the HVAC School Podcast.